Welcome back. Here we are, uh, recording this video about rational equations again. So we're going to do these two examples for sure because they have kind of a related thing. And then, I don't know if I'll do this one. Maybe I'll do this one. This one's a little trickier because it has complex fractions and it's a rational equation. So it kind of combines two of the things we talked about before. So let's start here though. So first thing I want to do is check my domain. And for this one, x can't be -5. For this one, x can't be 5. And for this one, x can't be plus or minus 5, which is actually what these two are. So really the domain is all the numbers except 5 and -5. So if I were to write that, and I am writing it, it would look something like that. So those are my domain restrictions, 5 and -5. I need to make an LCM. When I have like binomials or trinomials in the bottom, I list them out and I try and factor them if possible. This is the first one. This is the second denominator. And this hopefully you recognize as being x plus 5 and x minus 5. So this is x plus 5 and x minus 5. So let's build us a least common denominator. I'll start with the biggest, most complicated expression I have. Doesn't really matter where you start, but that tends to make things easier. So that one, I have both those factors in there. X plus 5 is already a factor of this, so I don't have to worry about it. X minus 5 is also already a factor, so I don't have to worry about it. So this is my LCD, x plus 5 times x minus 5, which is also known as x squared minus 25. Let's just keep that in the back of our minds. So if I multiply this whole equation by this LCD, I sometimes do it like this. I just imagine I multiply, it's written right here. I'm going to multiply this by both sides, by all three terms in this equation, and see what all the fractions ought to go away, and I'll see what I have left. So I multiplied this LCM. I'm going to outline it in red so you remember what it is I'm multiplying. If I multiply this LCM by the first fraction, the x plus 5s cancel out. I divide this by x plus 5 basically, and I'm left with this x minus 5. Multiply that by 2 times x minus 5. Now, same trick, this whole thing times the second fraction, and I get the x minus 5s cross off, the x plus 5 stays, multiply it by 1, and that's just x plus 5. I'm not going to write the 1. And now this thing times this fraction, the one on the right, this x plus 5, x minus 5, we know is equal to x squared minus 25. That's where we got it in the first place. So this fraction times, this LCM times this fraction, the whole numerator, this whole thing cancels out the entire denominator over here. And all I have left is 16. So that's a pretty straightforward equation to solve now, I think. You get, you distribute 2x minus 10 plus x plus 5 equals 16. So I get 3x minus 5 equals 16. So 3x is 21, so x is 7. So that's a reasonable number. If I look up here at my domain restriction to check it, this number 7 is not -5 or 5, so it passes that test. And like I said, generally, if it passes that test, it'll work, but we always just check to make sure. So I'm going to plug it in to each one of these x's in my original equation. I'll write that out, even though you don't always have to do this step if you can see what some of these numbers are going to be. I'm going to write it out just so you can see where I'm plugging it in. 25. So 7 plus 5 is 12, and 2 over 12 is 1/6. 7 minus 5 is 2, so that's a 1 over 2. And then I get 16 over 49 minus 25 is 24. So let's see if this works. I certainly hope it does. 1/6 plus a half is 1/6 plus 3/6. 16 over 24 is 2/3. All right, this was the question mark one. I should have done that all. Question mark, maybe. 1 plus 3 is 4, so I get 4/6 equal to 2/3, which is correct. These things are equivalent, so my answer is x equals 7. Okay, so that's how this works. I just wanted to kind of clarify how this one is a little different than the other ones. Like say this one, the denominators were monomials. In this one, they were binomials, but they were the same. And in this one, they're binomials, but they're different. So we have to the LCM gets a little more complicated, but the process is exactly the same. Check the domain, find the LCM, clear the fractions, solve the equation, and check it. So this one's very closely related to the last one. We will look at this and we will say, this is y plus 1. This is y plus 1 times y minus 1. This is 1 minus y, which we know is the opposite of y minus 1. So if we want to, we can rewrite this thing as negative y minus 1. Like negative 1 times y minus 1, basically. And that's going to help because now this one matches one that's over here. So to build my LCM from these, I do y plus 1 times y minus 1. I just took this whole denominator here. I check this. Do I have a y plus 1? I do. Look at this one. Do I have a negative 1 yet? I do not. Do I have a y minus 1? I do. So really, this is my LCM right here. Negative y plus 1 times y minus 1, which is also known as negative y squared minus 1. Remember, this y plus 1 times y times it's y plus 1 times y minus 1 is y squared minus 1. So we're going to multiply this whole LCD by everything in the equation. The y plus 1 cancels out with the y plus 1, but the negative and the y minus 1 are still there. So I'm going to write this as negative. Why am I doing it in red? I'm going to write it as negative 3 minus 2y times y minus 1. So just remember, I crossed off the y plus 1 and this y plus 1, but there was still a negative and a y minus 1. I multiplied both of those by the numerator here. Remember, divide and then multiply. Divide and then multiply. Divide and then multiply. Okay. If I look at this guy, it's a minus, and then I get this y squared minus 1 on the bottom is exactly what y plus 1 times y minus 1 is. So all of these terms cancel out with the y squared minus 1. The negative has to stay though. So this is really the 10, it's like really 10 times negative 1, which is negative 10. So I'm going to write that as plus 10. It was like minus negative 10 becomes plus 10. And now when I cancel these out, remember this was 1. This is like y plus 1 times 1 minus y. That's what this thing is equal to. So I can just cross off the 1 minus y's and I get 2y minus 2y plus 3 times y plus 1. And I'm going to solve this, but before I do, I'm going to go back because I skipped the first step of determining the domain. And I can see from this one, I'll get y can't be negative 1. From this one, I get y can't be positive or negative 1. From this one, I get y can't be positive 1. So my domain is all the x's that are not equal to negative 1 and 1. And you guys know how to write that in interval notation, but I'm not going to bother doing it right now. So let's just multiply this stuff out. So negative 3y minus 3 minus 2y squared plus 2y, which is, okay, plus 10. This is 2y squared plus 3 plus 2 plus 5y plus 3. 3y and 2y is 5y. Well, let's do this first. Negative 2y squared is positive 2y squared. 3y and 2y is 5y, but negative that is negative 5y. And then negative 3 is plus 3, plus 10 also is plus 13. 2y squared plus 5y plus 3. The 2y squares cross off. I subtract it from both sides. I'm going to add 5y to both sides. So this goes away and this becomes 10y over here. And I'm going to subtract 3 from both sides. This becomes 10, which means y equals 1. It's a nice round number. I go back and I check it and ooh, if I check that, I can see this is a problem. The x can't be 1. Did I write x? That was silly. I should have written y up there. I see when I check with my domain restriction that y cannot be equal to 1, which means this does not work, which means there's no solution. So here we will. I can do this one, and then we're going to be done. So it says find any values of a for which f of a, which is this one, equals g of a, which is this one. I know these are x's and those are a's, but it doesn't matter what the variables are named. The f and the g are what are the important variable names here. So this could just easily say find any values of x for which f of x equals g of x, and it means the exact same thing. So basically you set these things equal to each other and you solve for x. That's what this is saying to do. So I'm going to say 2 minus x over 4 over 2 equals x over 4 minus 2 over x over 2 plus 2. This is really not actually a rational equation technically, but this x down the bottom means that something funky might happen. So just based on this, none of my denominators specifically have restrictions, except like the denominator of this is just 4. So that is always 4. I don't have to worry about that. The 2 doesn't have a denominator. This doesn't have a denominator. This denominator is 4 again. No denominator. This one is x over 2 plus 2. Again, none of the denominators of the individual fractions have x's in them, but this denominator does. If I think about this thing, x over 2 plus 2 is the denominator, that can be equal to 0. So I'd see if I do x over 2 plus 2 equals 0, I get x over 2 equals negative 2, which means x equals negative 4. So this is a restriction. Because if I plug negative 4 in here, I get a 0 on the bottom of this fraction of g of x. So this is going to be my only restriction. And what would be a good thing to do here to solve this would be to make it so that these expressions, which are currently complex fractions, are not complex fractions. We basically spent all day, I say today, but it's really going to be on Wednesday. Wednesday? Oh, yeah, Wednesday. We spent all day Wednesday talking about how to simplify complex fractions. So if I look at this first one, I can see that the common denominator is going to be 4. So I'll multiply the top and bottom of this one by 4. And the same thing here. So 4 times 2 is 8. 4 times x over 4 is just x. That's going to be an 8 here. And 4 times x over 4 is x. 4 times 2 is 8. 4 times x over 2, well, 4 divided by 2 is 2 times x is 2x plus 8. So now the question is, are there any answers to this that worked where x does not equal negative 4? Sure, there's probably a lot of ways to solve this. My favorite way is what I call cross multiplication. That drives some math teachers crazy, but I do it anyways. I'm just kind of a rebel like that. I do this times this equals this times this. 8 minus x times 2x plus 8 equals 8 times x minus 8. I'm glad this is the last one we're doing. So let's see, 16x plus 64 minus 2x squared minus 8x equals 8x minus 64. Nothing cancels out. That's super. So, right. Actually, this 16x minus 8x is 8x plus 64 minus 2x squared equals 8x minus 64. I just combined these two like terms. And now the 8x, if I subtract 8x from both sides, those go away. So I get negative 2x squared equals negative 128, which means x squared equals 64, which means x is plus or minus 8. And that is not one of my restrictions, so that checks out, which means hopefully both of these numbers are going to work in the original. I am not going to do that right now because I don't want this video to be any longer, but I am going to ask you guys to check it and make sure that it works. I'm going to ask you guys to submit that to me. At least I'm going to come around and look at everybody's check of these two numbers in this in the originals here before before we begin work on this in class. So hope this was informative. I'll see you guys on Wednesday.